Okay, cool. I think we're recording. All right, wonderful. So informally, an optimization problem seeks to find the best value of a decision variable x subject to some constraints. Okay, so when we say decision variable, all that we mean is that's the variable that we're looking for the value of, right? So say like I was trying to optimize my water bottle to hold, the most water while having the least amount of mass. Okay, so maybe my decision variables would be something about like the circumference or the height of my water bottle in that case. Okay, so we're using this term like optimal over here, but we actually have to assign some meaning to that if we want to write this more mathematically. Okay, so if we want to define what it means for something to be mathematically optimal, we use a cost function. And this is a function of the decision variable that tells us how good it is. Okay, so usually we'll use f of x, or j of x is another common variable that's used a lot in control. All right, so if x is good, like that's a really good variable, it's very optimal, we know that f of x will be small. Okay, the cost will be low if we have a really good value of x, but if x is bad, I'm sure you can guess that f of x will be large, right? Will be large. Okay, so this function is something that tells us how good one of these optimization variables x actually is. All right, you can just think of it like it's going to cost you a lot if you have a really, really large value of this thing. Okay, so let's try and develop a little bit of standard notation for dealing with these optimization problems. All right, so our notation that we're really going to use a lot is the following. All right, so I'm just going to write this out for now, and then I'll come back and explain what it means in just a sec. All right, so we're going to say x star equals r of min over x element d f of x such that, sure, let's say g of x is less than or equal to b, and a of x less than or equal to c. Okay, so what all these different terms actually mean up here, right? So what we're saying over here is that when we have this min over x element d, right? Like what does this little part mean over here? This means that we're looking for the minimum of f of x over all values of x in some domain d. Okay, so that's why we have that little x and d over there. We're searching over all different values in our domain, and we're saying, okay, we want to go ahead and find the minimum of that. Now, what does this arg part mean, right? So this arg tells us that what we're actually interested in this optimization problem is not the minimum value of f itself, but the value of x that makes that minimum happen. All right, so arg is the argument. So it's saying that, oh, okay, we're going to solve this problem, we're going to find our minimum value of f, but what we actually want to return is the argument, right? The value of x that causes this optimization condition to happen. All right, so we denote the actual optimal value of x with this little star up here. So we have x star, that's our actual optimal value. Okay, and down here, right, we have ST. So that stands for subject to or such that. Okay, and this is where our constraints for our optimization problem are. Okay, so we don't just want to find the minimum of this function f of x in a vacuum, right? We want to keep some different constraints in mind. So we're going to say, okay, we want to optimize this, but at the same time, we're going to have this constraint on x that this other function g of x needs to be less than or equal to b. Okay, now we're also going to have this other constraint. Let me make this an equal sign over here, that a of x equals to c. Okay, so we're looking for all values of x that satisfy these constraints. All right, and over all those values of x that satisfy these constraints, we want to find the smallest value of f. Okay, so these constraints are things that x must satisfy. All right, so if the value of x, minimizes f, but it doesn't satisfy these conditions, it doesn't solve this problem. All right, So in general, we have two different types of constraints that you'll use a lot. So if you have like a less than or equal to, that's usually called an inequality constraint. And if you have a pure equals to, like we have in the second condition, that is an equality constraint. Okay. So overall, just remember, we're trying to minimize this cost f subject to these two constraints on our variable x. Okay. And just note that our constraints must be a function of x. A function of x. All right. Because if they're not a function of x, right, they're just other random constraints, they don't actually have anything to do with this optimization problem. Right? This whole problem is that we're searching for this value of x. Right. So if these two things aren't constraining x, then there's no real point in having. All right. So do we have any general questions about this setup for this optimization problem? Like why do we like using this notation? What is good? What do we think? All right. Very cool. So it turns out that in control, we really, really like framing things as optimization problems. All right, optimization is great. It's a big friend of the field of control. And it's really especially useful in this idea of model predictive control. Model predictive control. Okay, so just as a quick show of hands, how many people have heard of this thing before? Wow, wonderful. All right, any MPC enthusiasts in the audience? Okay, great. So if you want to get hyped, talk to front end. All right, wonderful. So what is model predictive control? All right, so our main question when developing MPC is, can we formulate an optimization problem to solve both control and path planning? Right? So at the moment, sort of in our class, right, we just finished this whole unit on control, right? We talked about all these great nonlinear feedback controllers. We're now sort of transitioning into this path planning focus. So it turns out model predictive control actually bridges the gap between these two parts really nicely, and it's going to enable us to solve both of these problems just with a single optimization. All right, so it's super, super powerful, and it's very flexible, we'll see as well. Okay. So, what happened?
Sorry, what is it? Oh, both.
Both. Sorry, yeah. All right. Yeah, thanks. All right, great. Okay, so we could start out by just discussing a general setup for these problems, right? So before last week, we were talking about feedback linearization, but we were really just focusing on these continuous time, control affine systems, right? And that was pretty good. Like a lot of robotic systems are control affine, so that's all great. But if we want to make things actually like fully general, right, we're gonna have to focus on the full general nonlinear case. And this is something that MPC actually deals with really, really well. Bless you, man. All right. So we're gonna say, suppose we have a discrete time system, and it's going to be a nonlinear system. X, k plus 1 equals f of x of k, u of k. All right. So something that's important to note is that this is sort of one of the first controllers we're developing that's actually directly a discrete time, right? All of ours so far have been for these continuous time systems where we have x dots instead of xk plus 1s. So we'll sort of see like why we need this discrete time assumption in a little while. But if you want to apply it to a continuous time system like a robot, if you guys remember from your homework 1, there was that question on discretization, right? So you could use those methods like Euler discretization or like RK4 to convert these actually continuous time systems into equivalent discrete time ones. Okay, so you can discretize continuous time system as needed. Okay, wonderful. Yeah, what's up?
The argument for the x, like x.
Oh, that's a k plus 1. Thank you. Yeah, my right hand is not on it today. So yeah, any other questions? Okay, very cool. So just as a quick sort of shorthand for these discrete time systems, we're going to be dealing with these xk, uk, xk plus 1 quite a bit. So just to sort of shorten this notation, I'm going to write this as x subscript k plus 1 equals f of x subscript k uk. It's just going to be a little bit nicer for us to work in. And I think, yeah, we're going to be writing out some kind of long cost functions in a little bit. So it's going to save us some a little bit of a headache. Okay. So what we're going to say now is, let's start at an initial condition x of 0, okay? And we want to drive our entire system, right? This xk plus 1 equals fk uk. We want to drive it to a desired state xd, okay? So say I'm starting over here and I want to go over there to college, right? So I want to come up with some sort of sequence, right? So on the screen time that steps me over to there. All right. So what we're going to do, right, is we're not just going to think about this as a control problem, but we're also going to think about it as a path planning problem. All right. So not only do I want to figure out the optimal sequence of inputs to get me over there, but I want to figure out the optimal sequence of states as well. Okay. So our question is, we want to find an optimal path of n steps. It's going to be x0. Actually, it's going to be n plus 1 steps. So x0, x1, all the way through xn, and an associated sequence of inputs u0, u1, through un that allow us to follow the path. And we want this path to be such that it ends up as close as it can possibly be to the goal state once we're at xn, okay? So we want xn to be close to xd. All right, wonderful. So what's this actually going to look like in practice? So we can sort of reason about it with like a little turtlebot example. Like if we have x0 over here and then xd, maybe we'll have like some sort of optimal path that's generated that kind of looks like that, right? And along the way, maybe that'll be our x1, our x2, x3, and so on. Maybe our xn will end up pretty close to xd, but maybe not exactly at it. All right? Yeah. So you could actually have it be either, but we're just going to be talking about it as just like a straight up set. And yeah, sure. Because MPC is actually going to generate the trajectory for us. So the MPC algorithm will actually be generating all of these intermediate points for us. So it'll give us the trajectory. Yeah. Yeah, so it's sort of like U is, yeah, so we have like a UN over here, right? Is that what you mean? So U naught is the input that takes us from X naught to X1. So yeah, so x0 is given, and then we're saying, okay, when we're at x0, we're going to find an input u0 that takes us to x1, and then so on like that. Yeah, that's a good clarification. Thanks. u2, and then so on. Yeah. All right, great. So, oh yeah.
When the optimization happens, are you trying to like minimize energy? Is that the main?
Yeah, so we're going to talk about what we want to like actually minimize in just a sec. Energy is going to be one of them, but yeah, well, so we're gonna talk about our decision variables first, and then we'll put together our cost function. But yeah, wonderful. Yeah, any other questions? Good. Yeah, what's up? Yep. Yeah, so we're going to do a little bit of a demo of how to deal with that a little bit later. Yeah, I'm glad you're thinking about that now. Okay, wonderful. So let's set up our optimization problem. So remember, we had those three different parts. So we had our decision variables, we had our cost function, and then we had our constraints, right? So we'll just go ahead and start with the decision variables. So step one, our decision variables. Okay, so remember, these are actually what we want to optimize, right? So in this case, we're looking for an optimal sequence of states, and we're looking for an optimal sequence of inputs, okay? So that just means that our decision variables are going to be x0, x1, through xn, and u0, u1 through un minus 1. Oh, yeah, that should be n minus 1 up there. Okay, so I'll just refer to this general sequence as x up here, and this general sequence as u down here. All right, so these are what we're actually searching for in our optimization problem. All right. So we want these. All right, so that brings us to step 2, which is our cost function. This is a really important one. This is what's actually going to determine the behavior of our MPC. Okay, so Jackson brought up a great point, and he said that one thing that we want to minimize as we're going along is the energy, right? So when we wrote out that CLF-QP program, right, the cost function was minimizing the energy that we're putting in the system. So right here, what we're going to say is that at each time step, right, for each input that we have in here in this sequence, we want each input to be the minimum energy input. All right. So one term in our cost function is an energy term, right? So we could say that, you know, ui times some matrix R times ui will be one term. Okay. So here, R is going to be a positive semi-definite matrix. All right, and that means that R is symmetric and has all eigenvalues greater than or equal to 0. Okay, so all that this positive semi-definite thing means is that when we actually take ui transpose R ui, it's like a weighted version of just the magnitude of ui squared. All right, so it's just like we're weighting different components in that magnitude a little bit different. That's all that we're changing here. You could really think of it like, okay, you know, we're just trying to minimize the size of this vector. Okay, so do we have any questions about this term or what I mean by weighted when I say that? Yeah.
I didn't quite get how minimizing UI minimizing energy.
Yeah. So it's like the energy we're inputting into the system, right? So if I have like my water bottle over here, right? I'm trying to move it over there. I could jerk it really, really fast, but I would be putting in a lot of energy into this. So instead, if we could find like some smoother set of inputs that go in, that's going to be minimum energy and it's going to give us a nice and smooth path as we're going along. Does that make sense?
How does minimizing UI minimize?
Yeah. So I think maybe it would help if I sketched it out with a little example over here. So if we had lambda 1, lambda 2, 0, 0, and we had a 2D input vector, u1, u2. If we calculate u transpose ru for this case, we're going to end up with lambda 1 u1 squared plus lambda 2 u2 squared. So by changing what the eigenvalues of that matrix are, we're changing like the different weights that we have assigned to each values of u. Okay. So if we set it to the identity, then we just get a straight up norm. But yeah, otherwise, yeah. Does that make sense?
Yeah.
Okay, cool.
Sorry.
Yeah.
So why was that a form of the units related to the energy?
Yeah, so you know we like quadratic forms because they're convex in general, so that keeps our optimization problem kind of like well posed, you could say. But yeah, it's really just that we're trying to like minimize the strength of our input that we're having in. Yeah, so it's not really like energy in the sense of like kinetic energy, potential energy, but it's more like what we're putting in. Yeah. Yeah, great questions. Any other questions? How are we doing, guys? Okay. All right, so that's our first term, right? That was energy, but what else do we want to minimize? Do we have any ideas? So as we're going along, like what do we want our sequence to look like? Yeah. Yeah, exactly. So we want distance, right? So we want our path to sort of be pointing in the right direction as we're going along, right? If we're not actually going towards our goal state, then it's no good. Okay. Is that a hand up? Yeah.
Maybe time.
Yeah, maybe time. Okay. So we could have a time quantity as well. Any other ideas? Did you have another thought, Jackson? Or...
I was saying like, I think it fits into the other category.
Okay. All right. Let me know if it comes back up. Okay. So we also want to minimize distance as we're going along. All right. So what that means is that we could sort of try to minimize xi, right, which is our ith state vector in our path as we're going along, xi minus xd transpose times some matrix, I called it Q here, yeah, Q times xi minus xd, all right? Where Q is also going to be a positive semi-definite matrix, okay? Because now it's like we're trying to minimize a weighted magnitude of xi minus xd, okay? So this is minimized for xi equals xd, all right? Bless you. So what we're really trying to do is we're trying to make sure that each term as we're going along remains really, really close to where that desired state is, or at the very least, it's sort of going along in that direction, okay? All right, so that's one more term. And then, yeah, so we could really roll time into that one and then the input weighting as well. Yeah. All right. So we have one more point, which is our final distance. Okay. So, this constraint is great for really going ahead and making sure at each step along the way. Yeah.
What if, like, to minimize energy, it takes a really short distance, but it just goes like extremely slow?
Oh, yeah. Yeah, I mean, that'll be something more that you have to tune yourself. Like, you ultimately have to decide what you want in your system. So that's more of a design choice. But yeah, it's pretty flexible in general, I'd say. Yeah, yeah. All right. So something else that we'll also try to minimize a little bit separately from the rest of our input sequence is the final distance, okay? So xn minus xd, which is the last term in our sequence, okay? Final term. We'll have transpose times some matrix P times xn minus xd, where P will be another positive semi-definite matrix, okay? And a lot of the times we like tuning this final term separately because, as we're going along, we might want certain input dynamics or certain state dynamics, right? We might like certain behavior in our path. But ultimately, we really, really do want to encourage the endpoint of our path to be very close to where our goal state is, okay? So we just like to tune this separately from the rest of the sequence. Okay. Does anyone have any questions about why that is? It's a little bit of a subtle point, but it's just, sometimes we don't really care about how our intermediate behavior is so much, right? We don't want super aggressive behavior as we're going along, but we really want to ensure that ultimately at the end point, we are pointing in our direction. Yeah. So if I understand this correctly, are you solving for all xi under one optimization problem? So it'd be like a sum. Yeah, we're going to take the whole thing under a sum. Yeah, so that's our next step. Yeah. All right. Any other questions? Yeah. You don't have Q and P. Are you still minimizing this system? Yeah, so Q and P is just to weight certain terms more than others. So let's say, for example, that the first term in our vector wasn't converging, but the rest of them were. What we could do is we could weight the first term in that vector much higher than all the others. So that way it's prioritized by your optimization because it has much more cost assigned to it. Right, am I understanding correctly that xi minus xd transpose xi minus xd? Yep. That's still minimized because the desired point of the. That's right. That's right. So we could just prioritize like one of those variables more than others in the optimization. Yeah. Sure. Okay. All right. Very cool. So yeah. So someone had just mentioned, right, that at the moment we're just looking at all these things like separately, right? So what we actually have to do now is we have to go ahead and sum over all of these different terms. Okay. So let's just add them up. Add them up. Nice. So we're going to say that our total cost, which I'll just label J in this case, is going to be our final distance term, right? Xn minus xd transpose P, xn minus xd, plus the sum from k goes to 0 up to n minus 1 of xk minus xd transpose times q, xk minus xd. And then we're going to have our input term as well. So UK transpose R UK, all right? So just to clarify, there's some little brackets around this whole thing. Okay, so what we're doing is we're saying, okay, we knew that these guys were what we wanted to minimize at every step, all right? So all that we're doing is just summing over every step in our path. Over every step in the path. All right. So if we account for what's happening at every step along the way, right, we're adding up the cost for all these different steps, then we'll be able to be optimal at every step. If we all right. Does that make sense to you guys? Are you seeing where this sum comes into it? You just want to account for every step in there. All right. So I know this cost function is a little bit of a handful to write out, but it actually turns out to be really nice for us, and it's going to give us some really great properties. Okay. All right. So let's move on to the constraints, the optimization.
So the xn minus xd is just like how close you end up getting.
Yeah. So that's just that we wanted to separately weight that final term. So this is sometimes called the terminal cost. Kind of an ominous name, but yeah. Okay. Yeah, any other questions before we talk about constraints? Yeah.
So is there relative weight between like the terminal cost and the other stuff? Like, is that calculated by the matrices doing R, or can you like do another like scalar constant?
Yeah, so usually you would just pop that right in there. So if you wanted to have a scalar constant out front, that would be the same as that kind of speed. Yeah. So yeah, I mean that actually brings up a really good point about how you select these Q and R matrices, because I know it is a little bit arbitrary at the moment. So generally, what you do is, if you know your X is going to be within some range and your inputs are going to be within some range, you can scale the eigenvalues of these matrices such that those things are sort of normalized to be all in the same cost, despite these different values they might jump around to. Okay, very cool. So let's talk about constraints. So what are some constraints that we might want to have on our different optimization, right? Like xn, xk, that's what do we want? Any ideas? Yeah. Our system dynamics, right? Yeah, that's the big one. So whatever path we generate must respect our system dynamics, right? So it's great that, if we have like x0 and x desired over here, right? If we generate some straight line path like that, right? Wonderful. That's the shortest distance path between those two. But if our system isn't actually able to follow this perfectly, right, there's no point in having that path. Right? You may as well have not generated it if, say, our turtlebot isn't actually capable of executing that sort of thing. All right. So what we have to do is we have to add in our system dynamics as a constraint to make sure that this is a path that our system will actually be capable of following in the first place. All right. So how do we add this constraint? Well, we have like x0, x1, all the way through xn as our optimization variables, right? We have our same for inputs, u0 up to un minus 1. So our optimization constraint in this case would just be putting that in directly, right? Xk plus 1 is equal to f of xk uk. For 0 is less than or equal to k, is less than or equal to n minus 1. Okay, so just at every step along the way in this path, we're going to go ahead and enforce our system dynamics to make sure that whatever path we generate is actually feasible for us to track. Okay, and then we're just going to have one more constraint, just that our first thing over here in this path where we're actually starting is just going to be the same as the initial condition of our actual rope, right? Because we already know what our initial condition is. So we may as well just plug that in and have our path start there. Okay, so those are our two basic optimization constraints for the simple case of MPC. All right. So let's talk about the overall MPC problem, and then we'll go ahead and do a demo and talk about some of this stuff. Do you have a question? Okay. All right. So there is a couple of finishing points for us. So MPC controller. Right. So we now have this great optimization problem that we wrote out, right? We have our cost function, our variables, our constraints, all that stuff. That's good. We can plug it into a computer and solve. But how do we actually use that for control, right? So our first step in an MPC controller will be to feed in the current system state as the initial condition in optimization. Okay, so we're just going to say wherever we're starting right now, that's going to be my initial condition when I try to solve this optimization. All right. So next up, what I'm going to do is I'm going to solve our optimization problem. And that generates our optimal sequences, X and U. All right, so that's great as well, all pretty standard. So this is with a computer. And then after that, I'm going to do something a little bit weird. All right, instead of executing that entire, nice sequence of n inputs that I just generated, I'm only going to send the first input out of that sequence to our system. Okay, so send the first input in U to the system. All right, so I'm only sending the first one, U0, into the system. Then I'm observing where it goes. Then I'm going to go ahead and restart this process. All right, so I'm sending in this input, takes me to a new state. I read that new state, reinitialize my optimization problem, and continue doing this sort of solution procedure. Okay, so this is going to be our general procedure for how MPC works. All right, so we're solving an optimization at each state, executing the first step, and then recomputing the solution. All right, so we'll talk about why we have to do that recomputation in just a minute. But do we have any questions about this general procedure outside? Yeah. Why the X? Oh, yeah, because we want to be generating that path as we're going along as well, right? So at the moment, we're just giving it a set point, but we don't actually have any idea of what trajectory it's going to follow along. And also, if we have X in there, it allows us to encode things like obstacle constraints or limitations. Yeah. What's up?
So I know linear programs, like quadratic programs, and other like standardized optimization problems have solvers for them, but this doesn't seem like it can fit into a general form because of the system dynamics.
Right. Yeah. So if it's what do you call it? It's a linear system, then you could actually rewrite this as a convex problem, and that'll be your first homework question. Okay. But outside of that, there's an optimization solver called Casati, which has been a library that's been sneaking its way into a lot of your homework problems, but you haven't actually directly used yet. So you guys will also be getting an introduction to how to use that. Yeah, what's up? Yeah, so for a QP, you actually require that your constraint is affine in your dynamics to keep that way. So in general, we can't enforce that with this. But what you could do is you could have a time varying Jacobian linearization of your system, and then you could use that to guarantee it. But yeah. Yeah, so you could linearize it around your current point, and then you would have to add on some other stuff in there. So it wouldn't quite be around an equilibrium point. But yeah, there's some sneaky tricks that you could do. If you want to talk about it afterwards, then yeah, I'd be happy. Yeah.
After you solve for optimal U, why do you send it back?
Oh yeah, so after you solve for the optimal U, you plug it into your system, then you see where your system goes, and once you're at that new state, you resolve your optimization problem. So it's like you're treating that new state as your initial condition when you're solving this thing up here.
But if we solve the quadratic problem, we get all the X0.
Right. So we're gonna talk about that in just a sec. So I think just for the sake of time, I'll move on to the problem one explanation because I have a feeling that it'll answer a lot of the current questions about this procedure. Yeah. Okay. So problem one on the discussion worksheet. Let me check what it says. What do we want here? Okay. Yeah. So what are the pros and cons of a high value of n? Okay, so that's our first question. And then our second question is, why don't we execute the whole sequence? U sequence. Okay, so we're just going to talk about this in somewhat of a discussion format. There's not too much math that's going to go along with this one. But I do need 2 volunteers from the audience for a small demo. What do we think? Okay. Yeah. All right. Okay, great. So I need one of you guys to be an obstacle, and the other one's going to be the bull sticks.
I'll be an obstacle.
Those are the tough ones. Okay, so I'm going to be a turtle bot, all right? So I'm a turtle bot with a model predictive controller. And let's say that, we want to try and tune what this value of n is, right? How far into the future? Okay. Let's say I'm going to start with n equals 1. It's going to give me a really, really quick solution to my optimization problem. There's not much that I have to sum in. Okay. So what that means is that when I'm solving for this controller, right, it gives me back only one input and one state that I have to follow, right? If I follow through with that plan, right, I'll just move over here, right? And then I'll keep doing that. I'll keep doing that. But the reason that I keep going in this direction, right, is that I was aiming for him eventually, right? But I wasn't able to see far enough into the future to know that Punnett was right here. Okay. So I started over here and I was like, yeah, that's where I want to go. So I just moved one step in that direction. So I didn't have enough planning into the future to see that Punnett was going to be there and be in the way of my eventual trajectory. All right. So what's going to happen is if I increase n to say like 5, for example, right? Now I'll be planning 5 steps in the future instead of just 1. So we'll do 1, 2, 3, 4, 5. And I might not be exactly at the goal, right? But I was able to plan around him because I had that high value. Okay. So that's what that allows us to do. Okay. It allows us to plan further and further into the future. But the higher the value is, the longer our optimization. Okay. It's a little bit of a trade-off. Okay. So that brings us over to the second point over here, which is why don't we execute full inputs? Okay. So say like I'm starting over here, right? It's a really windy day. Okay? It's really, really windy. So I'm like being blown all over the place as I'm going over here, right? But my dynamics model, right? It had no knowledge of that. So when I solved this whole optimization problem and I got my sequencing inputs, that's an open loop sequence, right? It uses no information about my current state other than the initial condition. Okay. So as we're going along, right, I could get totally blown off the course and end up walking out right out of the door. Okay. So what we're essentially doing when we only execute that first input is we're making sure that we don't go too far off the open loop. Okay. So I'm just going to execute one, then replan using my current state information, and that way we can sort of close this loop. Okay. So by replanning and incorporating our new state information, we can essentially, have a closed loop feedback. Now, another thing is if Punnett was moving, move back and forth like this, yeah, it's really sneaky. He's going to block my pocket. Yeah. But if I start right over here, right, and I come up with a plan for this time, he's all the way over there. So I'm going to be like, great. This is going to work out perfectly with timing. Yeah. So, but he's moving. So when he comes back over here, this plan is no longer valid, right? So if we have a dynamic environment as well, it's also changing. What an actual optimal path will be something that changes. That's also my opinion. Okay, so if you want to get round of applause. So that's why we sort of follow this general procedure in model predictive control. All right. So let's just go ahead and skip to our final section here about more constraints in MPC. Okay, then we can finish things up there for today. So constrained MPC. Okay. So do we have any questions about the previous section before we get on to this? Yeah. Yeah. So as long as your constraint is a function of your optimization variables, it can be whatever. Which is kind of a nice thing about why this is so flexible and constrained. Yeah. Any other questions? Okay. Very cool. All right. So our MPC decision variables were X and U, right? So that means that if we're trying to write a optimization constraint for this MPC problem, right, we can make them any functions of these X and U, right? It's super flexible for us. That's pretty much anything we would need to know about our system, okay? So we can directly constrain values of X and U in our optimization. And this is going to be really nice because if we have something like an obstacle with a known position and a known shape, right, we could directly write a constraint that says, hey, don't put our X in that obstacle, right? So this MPC is actually going to allow us to really flexibly plan around all these obstacles in space, not have to worry about treating that as a separate path planning problem, okay? So it's going to be nice and easy for, treating this case where we have different obstacles in the environment. Okay. So we're going to move on to problem 3 on the discussion worksheet. And what problem 3 says is, oh, okay. So it says, suppose there are P circular obstacles. Obstacles between our turtlebot position which is x comma y, and our goal position, which is xd and oh, sorry, did something coming up bad in the board? Or
I know, I got circular.
oh, okay, yeah, thanks. Circular, yeah. And we have a goal position, x desired, y desired. Okay, so each obstacle has a center of xi, yi, and radius of ri. Okay, so what our environment will look like is a little bit like this. So we have our turtlebot over here, x comma y, and then we have our desired state, xd comma yd, and maybe we have all these different like circular obstacles floating around somewhere in here, right? So what we want to do is we want to use MPC to plan a nice trajectory around this thing and to make us converge to our goal position while avoiding all these obstacles at the same time. Okay? All right. So what I want you guys to try and do is find an expression for a constraint on turtlebot position xy such that the turtlebot avoids all obstacles. Okay, so there might be multiple constraints for this. They can, depend on the positions of the circle over here, your goal position, Ri, any of these quantities. Okay, so I'll give you guys 2 minutes to try that out, and then we will regroup and see how it goes. Yeah. What's up? You can assume the turtlebot's just a point for now, but yeah, it's a very skinny turtlebot.
So, X and Y in the same situation.
Yep, it's good.
Still seems really hard to like plug into whatever. I mean, maybe there's like a black box optimizer.
Yeah, that's what Kasadi's going to be. So pretty much you could just throw at any nonlinear optimization problem, and it'll try its hardest to give you a solution. Yeah, it's pretty nice. It's actually it's one of my favorite libraries. It's kind of magical. So, yeah, I think you'll like it. All right, let's just give it one more minute, and then we'll see how we're all doing. Okay. Okay, very cool. So let's talk about our solution to this optimization problem, or this constraint problem, rather. So do we have any ideas as to what our constraint might be? Any thoughts? Yeah, I guess call again.
Yeah, I was thinking that we just want the I guess the magnitude of the distance
Okay.
between the turtlebot point.
Okay.
And
So if I call this like Q turtlebot or something, and then
minus the center of the height circle.
sure, yeah.
is greater than or equal to R sub I.
Greater than or equal to
Greater than.
greater than R sub I. Yeah. So that's one way of writing it, right? So this way we can ensure that the magnitude of our distance. So if this is Q naught I, right, and it has a circle radius. All right. Oh yeah. So that's the obstacle. Yeah. Obstacle I. Yeah. Thanks. Yeah. And then we have our turtlebot position somewhere over here. Our Q turtlebot, right? We just want to make sure that that turtlebot is at a radius that is greater than Ri if we wanted to stay outside. Okay. So that's one way of writing this constraint. Another one, we could write it just more directly, like using a circle formula, right? So we could have like xi or and what do I have? Yeah, so x minus xi squared plus y minus yi squared is greater than ri. That's another way. Ri squared. That's another way of writing it. Yeah, just more directly in terms of the variables. But yeah, anything like this will work, and you can actually directly use this as an optimization constraint. It's super quick and easy, and yeah, it's quite nice to write up in code. Okay. So I think we'll leave it there today in terms of content, but if you guys have any further questions, yeah, I'll stick around for a while afterwards. Yeah, thanks for coming. Thank you.